All right, so this is actually take 2 of 29. The camera shut off, and so I lost my beautiful explanation. So here we go. I had a request for 29. It involves a solution with integrating with u-substitution. So this is to serve as a really detailed step of how to solve this problem, including how to do u-substitution. And hopefully it'll help serve as a refresher. All right, so we have the shape that we're going to do the 4 steps on to derive an electric field equation. It has length L and charge positive Q, and we are observing on axis at a location D, and this is in X. So we can treat this as point particles. And so what would happen to our field, we can see that they would just basically, we'd have a field that would be pointing to the right. So the r hat vector in this case would be 1, 0, 0. And we could see that this contribution from this end would be bigger than the contribution on this end, so we can observe what's going to happen. And that pretty much wraps up step 1. We've cut it into reasonable pieces. We have predicted the field and drawn it. Okay, so step 2, we need the contribution of one piece. By the way, in this problem, it does parts A, B, C, which I'm doing here, but really this is just stepping you through the process we've been doing in class. Okay, so what we can see here is that this distance, if we cut up these slices, we've got little slices of delta x of the entire rod. And so if we were to look at this r vector, this is going to be equal to observation minus source. And so this is equal to d minus L plus, oops, lost my train of thought, sorry about that. This is equal to L plus D (0, 0) minus x. And so we get that our r vector is equal to L plus D minus x. And at this point, I'm just going to go ahead and work in just the x components. So the distance is L plus D minus x, and I'm going to leave the vector off until the end. Okay, so we can plug that into the point particle equation. So E is equal to 1 over 4 pi epsilon naught Q over R squared. So here, this is going to go into our R argument, and then our Q will become a delta Q, which would be the charge contribution of each of the individual slices. Delta Q L plus D minus 2 quantity squared. And delta Q, as it relates to the total charge, is Q over L times delta X. All right, so we can plug that in here. And we get that delta E is equal to 1 over 4 pi epsilon naught Q over L times delta X over L plus D minus X quantity squared. All right, so now we want to go after the sum. So we're going to need to write this as a differential equation. dE is equal to 1 over 4 pi epsilon naught Q over L times dx over L plus D minus X quantity squared. Integrate both sides. E is equal to x equals, or integrated from x equals 0 to x equals L, 1 over 4 pi epsilon naught Q over L over L plus D minus X quantity squared dx. Okay, and of course we got this because we have 0 to L. All right. So we can bring out our constants in front. We need to simplify this integral first. So this is 1 over 4 pi epsilon naught q over L from x equals 0 to x equals L dx over L plus D minus X quantity squared. So this is not a straightforward integral. So it's not so much a table of integrals problem, and I wouldn't really want to do it by integration by parts, but this is a perfect candidate for u-substitution. So u-substitution is basically reverse chain rule, and you're going to use it to make your integral into something that you already know how to integrate, and it's pretty straightforward. A hint that you're going to need u-substitution, basically, if you can see something. So for example, in this case, I can see that if I could make this all my variable, that I know how to integrate 1 over x squared, or in this case it'd be 1 over u squared. So let's say that u is equal to L plus D minus x. Now it's not as straightforward as simply making this u squared. You now need to integrate with respect to u. So that means we need to find dx in terms of du, and we need to convert these integration bounds in terms of u as well. So we would know that d dx of u is equal to d dx of L plus D minus x. So du dx is equal to minus 1, and therefore du is equal to minus dx, and it would then follow that dx is equal to minus du. Okay, so now we know what to plug in for dx into our integral that we've set up. So now we need to adjust the integration bounds. So if u is equal to L plus D minus x, then at x equals 0, u is equal to L plus D, and at x is equal to L, then u is equal to L plus D minus L is equal to D. Okay, so now we have everything in terms of u in the integration argument, so we can go ahead and plug that in. So then our integral becomes 1 over 4 pi epsilon naught q over L integrated from u equals L plus D to u equals D minus du over u squared. And then let's just look at just the argument. So we know that 1 over u squared du is equal to minus 1 over u plus c, if in the case of a integral without bounds. So now let's plug in what we know back in, 1 over 4 pi epsilon naught q over L, 1 over u integrated from D to, or solved from L plus D to D. And so it is true that you could decide to sub back in for x at this point and then solve, but my Calculus 2 professor recommended if you're going to do the u conversion, you might as well just plug in the bounds in u. So that's what I'm going to do, but it's your choice. So we have E is equal to 1 over 4 pi epsilon naught q over L, 1 over D minus 1 over L plus D. Let's look at this. I'm going to multiply in some tricky ones. So we've got L plus D over D, L plus D, minus D over D, L plus D. So tricky one here and a tricky one right there. That gives us L plus D minus D over D, L plus D, which gives us L over D, L plus D. And now we can bring all this down and we get that this is equal to 1 over 4 pi epsilon naught. We can see that this L cancels that L, so we have Q over dL plus D. And this will be in positive X in the case of a positive Q, and then it would go, well, the direction would always be, or yeah, our hat would always be in positive X, and Q would drive if it would go against the grain. And if you wanted to just do a quick check, you'd see the units worked out. I'll also give a special case. We can see that if D is much, much larger than L, then you would have the argument dL plus D would be basically be D0 plus D, which is D squared, and so you get the point particle. So it all checks out. All right, so hopefully this was helpful in just giving a refresher on how to do integration by u-substitution. In terms of when to use what integration method, it just takes practice. And it's okay to need to refresh yourself from time to time. I don't have u-substitution on the tip of my mind unless I'm doing it on a regular basis. So